Chapter 6 is all about solving systems of equations, and this section is going to be very short, mainly because I'm going to tell you to go look somewhere else. You've probably seen systems of equations, and more than likely you've done them in their smaller form with two unknown variables. You'll be doing them with two unknown variables, but you'll also be doing some with three unknowns. And the reason I'm going to tell you to look elsewhere is you probably remember that we had two methods of solving these, substitution and elimination. But it gets a little bit harder for these, and since you need to be able to do both types, I'm just going to show you the easy way using the calculator. How we're going to solve these is by using something called an augmented matrix. And here is the augmented matrix for this set of equations. What you'll notice is I just took the coefficients off the variables and wrote them down. In other words, this is the x column, the y column, the z column, the coefficient column, sorry, not the coefficient column, the after equals column. This is equation 1. This is equation 2, and that's equation 3. When you write these in an augmented matrix, you have to make sure the x's, the y's, and the z's are all lined up. And if you're missing one, put a 0 in its place as a placeholder. And we can go back and forth. In other words, if I'm given this, I can easily get this, and if I'm given this, I can easily get this. Similarly, if I wanted the augmented matrix for this, it would just be this. Now, when describing the size of a matrix, we give the number of rows first, and then the number of columns. So this matrix is a 3 by 4 matrix, and this matrix is a 2 by 3. So, for actually solving these, what you'll want to do now is go off on YouTube and type in something like that, solve systems of equations using the TI-84 or using RREF, reduced row echelon form. In your homework problems, you're going to see this referred to as Gauss-Jordan elimination. But if you type this in, you'll find lots of videos on YouTube which have a lot of nice graphics using the calculator mock-ups. A lot better than I can do, so I'm going to send you there to actually learn how to do that, which is why this section is going to be so short. But once you've gone out and figured this out by finding a video that you particularly like, and you've gotten this in an augmented matrix, go and perform reduced row echelon form on this matrix. And what you should end up with is something that looks like this. And now I will walk you through a few examples because I haven't found any of these out here that actually walk you through the three cases I want you to know about this. If you look at this augmented matrix, what you're going to find is a nice diagonal of 1s here, everything else out here being 0. So in other words, remember this is the x column. So this says 1x equals -6. This one is the y column. It says 1y equals 3. And this one's the z column, which is 1z equals 5. And whenever that happens, which is the preferred case, we get our answer. We just write down these numbers and we are done. But let's try a couple of cases where that doesn't happen. And here's the first one. So the first thing I do is rewrite this as an augmented matrix. Like so. And then do the reduced row echelon form operation on it. In which case you should get this answer out. And when you do this and perform this operation, you will not get a negative 1/2. You will get a negative 0.5. In most of your matrix operations, we don't like decimals. So whenever you see a decimal answer anywhere in your matrix, hit math frac. It works just like it does with a regular number. It'll convert the matrix back to fractions. But in this particular one, if we look down this diagonal, we see we have a problem down here. If I retranslated this bottom line, I would get 0x plus 0y plus 0z equals 1, or 0 equals 1, which is a false statement. And just like with regular linear equations, whenever you get that false statement out, it means no solution. And you're done. The most difficult one you're going to run across is this. So let's do this one. We're going to set this up in an augmented matrix. And then I'm going to perform the reduced row echelon form operation on it. Which gives me this. And again, I have a problem because I don't have that nice diagonal of 1s. So let's reconstruct this bottom row and see what's happening. Okay, so 0x plus 0y plus 0z equals 0, or 0 equals 0. And in linear equations, whenever you got something like this out, you said there were an infinite number of solutions. And there are an infinite number of solutions here. We just have to be a little bit more explicit about them. And the way we're going to be more explicit about them is write every single possibility down with respect to z. So whenever you see something like this, this is kind of an automatic thing that has to come out. This is just the set of all numbers, or ordered pairs. We're leaving the z intact, and z is some real number. If it were a 2x3 matrix with only 2 variables, you'd start out like that. If it were a 4x5 matrix with 4 variables and you won't have any of those, we put the last variable in here and have 3 spaces here. But we're dealing with this case. So somehow we have to find out what x and y are in terms of z. And luckily, we have this reduced row echelon form matrix to work with. So let's reconstruct this. This says y minus z equals 1. Well, that's really easy to solve for y. We just move the z over here. It becomes positive when it does. And y equals z plus 1. Let's write that explicitly here. Now let's do the same thing with x. When I reconstruct this top line, x minus 3z, there's no y term here, equals 0. So when I solve for x, I get x equals 3z. And I plug that in the x location. And I'm done.